The second two-level combinational synthesis method we examine in this course is the Quine-McCluskey method. It is an exact method conceptually similar to the Karno's method. In fact, it uses the same reduction rule to generate prime implicants and similar criteria for identifying the set of prime implicants representing a solution. The difference compared to the previous method is that it is more systematic. Although it also relies on tables, it does not involve their visual inspection, but rather a well-defined approach based on comparing the rows and columns of those tables. Thanks to this feature, the method can be easily translated into an algorithm, implemented in a program, and thus executed automatically by a computer. As we have seen, the Karno method is easy to apply for up to 4 variables, somewhat more laborious for 5 or 6, and virtually impossible to use with a larger number of variables. In contrast, the Quine-McCluskey method is theoretically applicable to problems with any number of variables. In practice, however, since the two algorithms for generating and selecting prime implicants both have exponential complexity, the method is realistically applicable with reasonable execution times for up to 10 variables. Finally, 2 additional advantages of this method compared to the Karno method are: it supports the use of various figures of merit to evaluate the quality of the explored solutions as long as they are additive, whereas Karno's method relies solely on cardinality and secondarily on the number of literals. Moreover, it can be easily extended to the joint synthesis of multiple functions, as we will study in the upcoming lessons. Quine-McCluskey method, like Karno's method, consists of 2 main phases: prime implicant generation, during which all the prime implicants of the function are systematically derived, and prime implicant selection, in which a minimal set of prime implicants is chosen to cover all the ones in the onset, and thus to form a complete and optimized representation of the function. In Karno's method, both phases are carried out on the same table. That is the Karno map. As a result, the 2 phases are often combined during execution. It is common to directly identify in a single step the prime implicants that form the final solution. This is possible because essential prime implicants can be visually recognized, and the remaining minterms to be covered are typically few, making the selection process straightforward. This kind of optimization is natural for a human, thanks to our ability to visually process and reason about patterns, but it is much more complex to implement algorithmically for automated execution. At the opposite, Quine-McCluskey method maintains a clear separation between the 2 phases, where each phase operates on a specific table. Let's begin with the study of the prime implicant generation phase. This phase starts by organizing the minterms of the function into a list. Recall that minterms are implicants, each one covering exactly 1 element of the onset. The minterms are grouped based on the number of ones in their binary representation. Next, these groups are inserted in a table, ordered in increasing number of ones, with 1 minterm per row. Each row in the table consists of 3 columns: the label, which contains the decimal value of the minterm, the binary representation of the minterm, a marking field, which is initially left blank. Let's look at an example. Consider a function of 4 variables, a, b, c, and d, with an onset including 0, 9, 11, 13, and 15. Here is the resulting table. As you can see, there are 4 groups. The first group contains minterms with 0 ones in their binary representation. That's just minterm 0. The group for minterms with a single one is empty, so it is omitted. The next group contains minterms with 2 ones, such as 9, and so on. The table has the 3 columns mentioned earlier, with the 3rd column still empty at this stage. You may also notice that we've drawn horizontal lines only where needed, to visually separate adjacent groups within the table. We now proceed with the systematic generation of implicants. This step generates all possible pairs of minterms taken from 2 adjacent groups. For each pair, we apply the same reduction rule used in the Karno map method, namely A and Z, or not A, and Z is equal to Z, where Z is a product term and A is a literal. In the binary representation of the newly generated implicant, the bit position corresponding to the eliminated literal is replaced with a don't care symbol, typically denoted as a dash. Let's continue the example from earlier. The first pair we examine is 0 and 9. Since these two minterms differ in 2 bits in the same positions, that is, they have a Hamming distance of 2, no reduction is possible. Next, we consider the pair 9 and 11. These differ in only 1 bit in the same position, specifically the 3rd bit in their binary string. Therefore, we can generate a new implicant with binary representation 1, 0, don't care, 1. Let's briefly compare this with what we would obtain from the Carnot map. Minterms 9 and 11 are adjacent on the map. So, if we combine them algebraically, we obtain A, not B, not C, not D, or A, not B, C, D equals A, not B, D. As expected, the variable C is eliminated. We continue this process for all valid pairs, checking whether a reduction is possible based on Hamming distance. In conclusion, from the initial table, which contained the minterms, that are implicants corresponding to one-dimensional cubes, we have now generated larger implicants, each one representing a two-dimensional cube. A couple of important notes. Comparing minterms from adjacent groups allows us to identify all pairs with a Hamming distance of 1. These are the only pairs for which reduction is possible. On the other hand, comparing minterms from non-adjacent groups is unnecessary, since their Hamming distance is guaranteed to be greater than 1, and therefore no reduction can be applied. In this example, we can observe that the group of minterms with a single 1 in their binary representation was omitted. Consequently, the groups with 0 and 2 1s appeared adjacent, prompting an incorrect attempt to combine minterms 0 and 9, a reduction that unsurprisingly failed. Actually, the two groups are not truly adjacent, and their elements cannot be combined. Additionally, when a minterm is involved in multiple reductions, we are in practice replicating that minterm. This reflects the idempotent property of Boolean algebra, A equals A or A. For example, in our case, we can observe that minterm 9 participates in 2 separate reductions, one with 11 and another with 13. Finally, minterms that participate in a successful reduction, resulting in the generation of a larger implicant, are marked in the table. This marking serves to indicate that these minterms are not prime implicants, since they have contributed to the formation of a larger implicant, that is, with fewer literals. Returning to our previous example, we mark minterms 9, 11, 13, and 15, as they have each been involved in at least one reduction. We now continue by constructing a new table, following the same rules as before. Each implicant in this new table is assigned a label consisting of the list of all minterms that contributed to its generation. In our previous example, we obtained 4 new implicants of dimension 2, which are organized into 2 groups based on the number of 1s in their binary representation. At this stage, none of these new implicants is marked, as they have not yet been involved in any further reductions. We now continue the prime implicant generation phase, applying the same reduction strategy introduced earlier. The only difference at this stage is the presence of don't care symbols in the binary representation of the implicants, which must be handled appropriately. Specifically, in order to generate a new implicant from a given pair, the 2 implicants must have the don't care symbol in the same position, and the remaining bits must differ in exactly 1 position. That is, they must have a Hamming distance of 1 in the defined bits. Let's return to our example. The comparison between implicants 911 and 1115 does not lead to a reduction because their don't care bits are located in different positions. However, the pair 911 and 1315 does allow for a valid reduction, producing the new implicant 911 1315, that is a 4-dimensional implicant that covers 4 minterms. And so the process continues. As you can see, we have now generated implicants of dimension 4, starting from implicants of dimension 2. Previously, we had generated implicants of dimension 2 from minterms, which are implicants of dimension 1. In general, these steps are iterated multiple times. At each iteration, one literal is eliminated, effectively doubling the dimension of the implicants produced in that step. In conclusion, the algorithm we are studying incrementally increases the dimension of the implicants step by step through repeated reduction. You may have noticed that we generated twice the implicant 9, 11, 13, 15, represented by the binary string as one don't care 1. This is not a coincidence. In fact, when moving from implicants of dimension 2 to those of dimension 4, each new implicant is generated exactly twice. This behavior will occur similarly in all subsequent iterations of the generation process. Let me explain why, using the Carnot map. We can observe that from the two implicants 911 and 1315, we can generate the larger implicant 911, 1315. At the same time, starting from the pair 913 and 1115, we can obtain the same implicant again. So even though the implicant 9, 11, 13, 15 is derived twice, it will appear only once in the new table we construct. The prime implicant generation phase is repeated iteratively, as shown, until no new implicants are produced. At that point, all unmarked implicants are identified as the prime implicants of the function under analysis. Here you can see the full execution of the prime implicant generation phase on the example we've been using. As you'll notice, the process stops at the third table, which contains only one implicant. Since that implicant cannot be reduced any further, the expansion phase terminates. In other examples, the final table may contain several implicants, but in that case, all of them will either have don't cares in different positions or be at a Hamming distance greater than 1, which means no further combinations are possible. Looking across the tables we've built, we can see that the only unmarked implicants are 0 and 9, 11, 13, 15. These are therefore the prime implicants of the function, and we label them P1 and P2. We can now compute the corresponding product terms for these two implicants. P1 corresponds to the minterm 0, which gives the expression not A and not B, and not C and not D. P2, corresponding to 9, 11, 13, 15, gives the expression A and D. Now let's take a closer look at the algorithm, which is used to generate the prime implicants of a logic function. We start by building the initial table that contains all the minterms of the function. These minterms are grouped according to the number of ones in their binary representation. Then, we exhaustively compare all pairs of implicants in the current table. If a pair of implicants differs by only one bit, we apply reduction. We combine the two terms by replacing the differing bit with a dash, indicating that the variable can take either value. After that, we mark all implicants that were involved in a successful reduction because they've already been used. Next, we build a new table using only the newly generated, reduced implicants. At this point we ask, is the new table empty? If yes, it means no further combinations are possible, so we proceed to the final step. If not, we repeat the process from step 2 with the new table. Finally, we collect all the implicants that were never marked, meaning they were never reduced. These are the prime implicants, which form the essential building blocks for the generation of the solution. As we know, a Boolean function may also include a don't care set. The Quine-McCluskey method handles don't care conditions as follows. At the beginning of the prime implicant generation phase, don't cares are treated as if they were part of the onset. This allows for the generation of larger implicants than would be possible by considering only the minterms with value 1. However, at the end of the generation phase, any unmarked row in the final table, whose label consists entirely of don't care elements, is not considered a prime implicant, and thus it is discarded. Let's take an example. Consider a function with onset including 9 and 14, and don't care set including 7, 13, and 15. We proceed with the prime implicant generation phase. At the end of the process, all entries in the second table are unmarked. Now let's analyze them one by one. For the row 913, since 9 is part of the onset, this implicant is retained and we assign it the label P1. For the row 14, 15, 14 belongs to the onset, so we assign it the label P2. On the other hand, the rows 715 and 1315 consist only of don't care terms. Therefore, they are discarded. In conclusion, the two prime implicants identified in this case are P1, whose expression is A and not C and D, and P2, whose expression is A and B and C.